Hello everyone. Let's continue with our chapter, that is chemical thermodynamics. So disclaimer slide. The images used in our slide deck are for educational purposes only. We respect the intellectual property rights of the original creators and owners of these images. If you are the owner of any of the images used in this deck and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the images. So this is our index slides in which we have studied something, and we have to study from extensive and intensive properties, then state path functions, Gibbs free energy, criteria for spontaneity, relationship between Gibbs energy change and equilibrium constant, heat, laws of thermodynamics, and last Carnot engine. So extensive and intensive properties. So the properties used to define the state of a system are extensive and intensive properties. Intensive property, those properties that depend on nature of matter but do not depend on quantity of matter. For example, pressure, temperature, specific heat, melting point, etc. Second is extensive properties. Those properties that depend on quantity of the matter present in the system, not the nature of the matter, but on the quantity of matter. For example, internal energy, heat, total moles, volume, enthalpy, entropy, phase change, etc. Force is extensive property, but pressure is intensive property. Okay. So state and path functions. State functions, those functions which depend only on the state of the system, as the name says, and not on how it is reached to that state. For example, pressure, volume, temperature, change in the enthalpy, del H, and change in internal energy, del E, etc. Second is path function. So the functions that depends upon the path followed are called path functions. For example, work done, heat, etc. So Gibbs free energy represented by delta G. The maximum amount of energy available to a system during a process that can be converted into useful work is called free energy or Gibbs free energy. Under standard conditions of temperature, that is at 298 Kelvin, and pressure, that is 1 atmosphere, the free energy change for a process in which reactants in their standard state is converted into products in their standard state is called standard free energy change. So Gibbs free energy change and standard free energy change has this difference, that in the standard free energy change, the energy change are happening in which reactants and products are at their standard state. The change in the Gibbs energy of a system as a function of temperature can be calculated by the equation known as Gibbs-Helmholtz equation, given by this: delta G equals to delta H minus T delta S, where delta G is Gibbs free energy, that's measurement of useful work, and delta H we know the enthalpy change, T is temperature, and delta S is entropy change. The following cases are considered for delta G. So these are the three conditions. First, if delta G is positive, that is greater than 0. So in this case, this process will be known spontaneous. If delta G is negative, that is less than 0, it will be spontaneous process. And if delta G is 0, it will be happening at equilibrium. Okay. So criteria for spontaneity. In the determination of spontaneity, Gibbs energy criteria is better than entropy criteria because Gibbs energy refers to the system only, while entropy refers to both system and surrounding. Okay, that's why in the determination of spontaneity, Gibbs energy criteria is better than the entropy. For negative value of delta G, several conditions exist which plays an important role in deciding the spontaneity of the process. So here we are having a table in which 4 columns are present. First one is for entropy change, then enthalpy change. Third is for Gibbs free energy change, and last one is for spontaneity of a process. So if entropy change is positive and enthalpy change is negative, the Gibbs free energy change will be negative at all temperatures. And the spontaneity of a process will be spontaneous at all the temperatures. Now, if the entropy change is negative and the enthalpy change is negative, then Gibbs free energy change is negative at all temperatures, no change. And the spontaneity of a process is spontaneous at low temperature but non-spontaneous at high temperature. So we can see that there is a change in the spontaneity of a process when the del S and del H, that entropy change and enthalpy change, become negative. If they both become positive, then the Gibbs free energy change will be positive at low temperature and negative at high temperature. So process spontaneity will be spontaneous at high temperature. Again, delta S and del H is positive and del G will be positive at all temperature, and spontaneity for process will be non-spontaneous at all temperature. Then del G will be positive at all the temperature, and spontaneity for process will be non-spontaneous at all the temperature, because del G is del H minus T del S, right? So minus T del S and minus del S will become positive and del G will become positive. So it will become positive at all temperature, and the spontaneity for process will become non-spontaneous at all the temperature. So relation between Gibbs energy change and equilibrium constant. Relation between Gibbs free energy with reaction quotient and equilibrium constant are as follows. So delta G equals to delta G naught plus 2.303 RT log Q, where Q is reaction quotient, which expresses the ratio of concentration or partial pressure of products to the reactants at any point in the reaction. This is important, at any point in the reaction. And at equilibrium, delta G becomes 0. So delta G naught will be equal to minus 2.303 RT log K. Here K will come because K is equilibrium constant, which expresses the ratio of concentration or partial pressure of products to the reactant at equilibrium. And at equilibrium, delta G will also become 0. So delta G naught equal to minus N E naught of cell F. So in this equation, that is delta G naught can also be written in this way, where N is the number of electrons lost or gained by the metal, and E naught of cell is the standard electron potential of the cell, and F is Faraday's constant, having the value of 1F will be equal to 96,500 coulomb. Efficiency of the fuel cell can also be calculated by using the change in Gibbs energy. That is, it is given as delta G divided by delta H multiplied by 100. It is efficiency of any fuel cell. So now we will study about the heat. So what is heat? It is defined as the quantity of energy which flows between system and surroundings on account of temperature difference, right? So on when the temperature difference is happening, heat will flow, and heat is the quantity of energy that will flow between the system and surrounding. It is also a path function. Heat is a path function, that is, it depends upon the path followed by the process. Here is also some sign convention for heat. So heat will be represented by Q. So if Q is positive, heat is supplied to the system, and if Q will be negative, heat is lost by the system. Okay, this is a sign convention. Internal energy. E or U, represented by E or U. It is the total energy within the substance. So total energy within the substance is internal energy. That's as the name says. It is equal to sum of translation energy, vibrational energy, and potential energy, etc. We can only determine the change in internal energy by this formula that delta U will be equal to U2 minus U1. Okay. So at constant temperature, internal energy change will be 0. Internal energy depends on temperature, pressure, volume, and quantity of matter present. Okay. So let's move on to the second law of thermodynamics. The second law of thermodynamics tells us whether a given process can occur spontaneously and to what extent. It also helps us to calculate maximum fraction of heat that can be converted into work in a given process. The second law states that the entropy of the universe is continuously increasing and tends to a maximum. So this is the second law which says us that the entropy of a universe is continuously increasing and it will tend to a maximum point, maximum value. For an irreversible process, ds is greater than dq by t, and we can also write that ds is greater than or equivalent to dq by t. And this is the mathematical statement of second law of thermodynamics. So now we will study about Carnot engine. So Carnot in 1824 gave an imaginary reversible cycle which demonstrates the maximum conversion of heat into work. He actually proposed a theoretical heat engine to show that its efficiency was based upon temperatures between which it is operated. So temperature is very important in the Carnot engine. A Carnot cycle comprises 4 operations or processes, which are first isothermal reversible expansion, second adiabatic reversible expansion, third isothermal reversible compression, fourth adiabatic reversible compression. And this is the diagram of Carnot cycle. On the graph we can see that the x-axis denotes volume and y-axis denotes pressure, and these are the lines. So basically P1 V1 here, A point. From A point, if we come down, that increase in volume and slight change in pressure is isothermal expansion. At B point, the pressure will become P2, volume will become B2, and from B, a sudden change in the pressure and a slight change in volume will happen, and we reach at point C where the pressure is P3 and the volume is V3, and the process of adiabatic expansion. Then from C, we go to the D point by sudden change in the volume and slight change in the pressure. And at point D, the pressure is P4, volume is V4, and the process was isothermal compression. And from the D, we again go at the starting point, that is A, and the process follows as adiabatic compression, and pressure is suddenly changes and the volume is slightly changes. So this is the Carnot cycle representing the different type of expansions and compressions happening in it. Net work done in the one cycle is given by W equals to RT2 ln V2 by V1 plus RT1 ln V4 by V3. Net heat absorbed in the whole cycle is Q, that is heat, equals to R T2 minus T1 ln V2 by V1. Efficiency of a heat engine, which is denoted by this symbol in a Carnot cycle, is given as this symbol is called as eta. So eta equals to W upon Q2, work done upon heat exchange, which can be written as T2 minus T1 upon T2, and on dividing with this is the final formula, that is 1 minus T1 by T2, where T1, T2 or any other term are absolute temperatures at different stages of the cycle. The above relation was stated in the form of Carnot theorem by the Carnot, that is every perfect engine working reversibly between same temperature limits has same efficiency, whatever be the working substance. Okay, so this is the statement given by the Carnot states about the perfect engine working and the efficiency of it, and it is known as Carnot's theorem given by the Carnot. So now the third law is third law of thermodynamics. So this law was proposed by German chemist Walther Nernst, and according to this law, the entropy of a perfectly crystalline substance approaches zero as the temperature approaches absolute zero, that is 0 Kelvin. It forms the basis from which entropies at other temperatures can be measured. So limit T from T to 0, S entropy will be equal to 0. So as the temperature approaches absolute 0, the entropy of a perfect crystalline substance will also approaches 0. This is the third law stated by Walther Nernst. Types of processes. So where the state of a variable can be changed by means of a thermodynamic process. And these are the following types. First, adiabatic process, in which system does not exchange heat with its surroundings. So system does not exchange heat in the with its surrounding is adiabatic process. That is, dQ will be 0. In the isothermal process, the temperature remains fixed. That is, change in the temperature will become 0. Third, isobaric process. In this process, change of state is brought about at constant pressure. That is, change in pressure is 0. In the fourth, isochoric process, volume of the system remains constant. That is, change in the volume will be 0. Fifth, cyclic process. So this is the process in which a system undergoes a number of different states and finally returns to its initial state. Okay, after a different change of state, it finally returns to its initial state in the cyclic process. For such a process, change in internal energy and enthalpy is 0. That is, dE or du equals to 0 and dH equals to 0. Reversible process. In this process, quasi-static system, change taken place is infinitesimally slow and their direction at any point can be reversed by infinitesimal change in the state of the system. Reversible process is an ideal process, and here every intermediate state is in equilibrium with others, if any. Okay, so this is reversible process. Seventh and last is irreversible process. This process is the one which cannot be reversed. In this process, amount of energy increases. All natural processes are irreversible in nature. Okay, so in the irreversible process, the reversible reaction cannot happen. That is, process can't be reversed. And in this process, amount of energy increase, and all the natural processes happening around us are irreversible in nature. There are some notes. First, if macroscopic properties like temperature, pressure, etc. do not change with the time, the system is said to be in thermodynamic equilibrium. Second, if two systems are in thermal equilibrium with a third system, they must be in thermal equilibrium with each other. This law is known as zeroth laws of thermodynamics, and it is important. Third, the law defines the temperature as the property which determines whether the body is in thermal equilibrium or not. So these are some note points we have to remember and we have to keep them in mind. Okay, so we are at our summary slides. So we have studied that energy transferred when a force is applied over a distance, and which is known as work. And entropy change is a measure of the disorder or randomness in a system. Del S is equals to Q equilibrium upon T for reversible process. Zeroth law states that if two systems are in thermal equilibrium with the third, they are in equilibrium with each other. First law states that energy cannot be created and destroyed. That is del U equals to Q plus W. Second law states that in any energy transfer, total entropy of an isolated system always increases. Third law states that as temperature approaches absolute zero, the entropy of a perfect crystal approaches zero. Kirchhoff's law connects changes in enthalpy or internal energy to the temperature. Gibbs free energy combines enthalpy and entropy to predict spontaneity of a process. And Carnot engine is an idealized heat engine that operates on a reversible cycle between the two heat reservoirs. And here this term will not come, so it will be only Q divided by T. Okay, thank you.